You ever really stop and think about how we name the great ages of human history? It's not after great leaders or empires or even big ideas. It's named after stuff, the materials we use to build our world.
That's right, the Stone Age, the Bronze Age, the Iron Age. It's kind of wild, isn't it? Our entire journey as a species is fundamentally tied to our ability to find, understand, and use the materials around us. Without that, we'd still be back at the very beginning.
So let's dive into this, because that connection between materials and technology has never been more vital. Today, we're going to get into the world of engineering materials and the art of picking the absolute perfect material for the right job. We're going to start with what makes any material tick. Then, we'll break down the four major families you see here: metals, ceramics, polymers, and composites. And we'll finish by looking at where this is all going, how we're shifting from just finding materials to actively designing them. Let's get into it.
Okay, so first things first, how do engineers even begin to choose from the thousands of materials out there? Well, it all boils down to one foundational concept, something often called the materials paradigm.
And here's the key takeaway. It's a four-way relationship between a material's internal structure, how we process it, the properties that result, and finally, how it performs. You simply cannot change one of these without affecting all the others. Think of it like baking a cake. If you change how you process it, say the oven temperature, you change its internal structure, right? That changes its properties, like how fluffy it is, which ultimately decides its performance, how good it tastes. This interplay is the master key to engineering matter.
So you can basically sort the entire world of materials into these four huge families. First, you've got metals, our strong, reliable workhorses. Then you have ceramics, the super hard materials that can take insane amounts of heat. Then there are polymers, your lightweight, versatile plastics and rubbers. And finally, composites, where we mix and match materials to get unbelievable performance, like in a carbon fiber bike that weighs almost nothing.
So let's jump into our first category, metals. They're the literal backbone of our world, from skyscrapers to the car you drive. But here's a fun fact. Most pure metals are actually way too soft for those jobs. That's why we create alloys, mixing metals to make them stronger. But how does that even work?
The secret is something called a solid solution. And it's pretty much what it sounds like. You know how you dissolve sugar and water? Imagine doing that, but with two solid metals. You're literally dissolving atoms of one metal into the crystal grid of another. But, and this is a huge but, you can't just throw any two metals together and cross your fingers. Nope, there's a recipe for it, laid out by a guy named Hume Rothery. And his rules are pretty straightforward. First, the atoms have to be about the same size. You can't mix a bowling ball and a marble. Second, they need to have similar crystal structures, the same basic atomic shape. And third and fourth, they have to be chemically compatible. When you nail this recipe, you get everything from the ridiculously lightweight aluminum in an airplane to the stainless steel in a surgeon's scalpel. Okay, up next, let's talk ceramics. And when you hear that word, I bet you're thinking of a coffee mug or a dinner plate. And you're not wrong. That's where the story started. But the modern world of ceramics, it's on a whole other planet. We are talking about some of the most advanced materials in existence.
The name itself might come from the Greek word for pottery, but the story took a massive leap forward in the 20th century. A quantum leap, really.
And just look at the pace of that change. It's stunning. In just over 50 years, we went from perfecting things like high-purity alumina in 36 to inventing bioceramics that literally fuse with human bone in 69. We figured out how to use over 24,000 ceramic tiles to protect the space shuttle from burning up on re-entry, and by 88, we were discovering ceramics that could conduct electricity with zero resistance. It's just an incredible rate of progress.
So yeah, this isn't your grandma's pottery. What you're looking at here is a machine, a microscopic machine made of ceramic. It's part of a system called MEMS, for microelectromechanical systems. These tiny ceramic engines are doing real work, pumping fluids, filtering particles, at a scale it's hard to even imagine. These advanced ceramics are nothing short of wonder materials. All right, on to our next big category, polymers. So, if metals are the strong backbone and ceramics are the tough shield, then you can think of polymers as the ultimate shapeshifters. These are the building blocks of all plastics and rubbers. So what exactly is a polymer? Well, the best way to visualize it is to picture a giant bowl of spaghetti. At the molecular level, that's what polymers are. Just really, really long, repeating chains of molecules. The true magic is that by engineering these chains, how long they are, how they're tangled up, we can create materials with a massive range of properties, from super stretchy to rock solid. And you know these materials intimately, even if you don't know their names. The humble milk jug? That's polyethylene. The PVC pipes inside your walls? That's a polymer. The lightweight polystyrene packaging that protects your new electronics? Yep, that too. Even the polycarbonate that makes your eyeglasses shatterproof. Polymers are, quite simply, everywhere.
So, what happens when one material just won't cut it? What if you need something that's both incredibly strong and incredibly lightweight, or something that's both tough and heat-resistant? Well, that's when you turn to our final category, composites.
A really great way to think about a composite is to picture reinforced concrete. You've got concrete, which is strong when you squeeze it, and steel rebar, which is strong when you pull it. Put them together, and you get a material that's strong every which way. Composites are that exact same idea, just often happening on a microscopic level.
Every composite has two stars of the show. You have the matrix, which is basically the glue holding everything together. And then you have the reinforcement, which provides all the strength and stiffness, usually in the form of tiny, powerful fibers. A perfect example is fiberglass. You take strong but brittle glass fibers and mix them into a flexible plastic resin. The result? You get the strength of glass without the brittleness, creating a tough, lightweight material that's perfect for things like boat hulls or surfboards. The best of both worlds.
So we've seen the major classes of materials, but for most of human history, finding new materials was just a slow, painful process of trial and error. That whole system is being flipped on its head. We are now entering an era not of material discovery, but of material design.
This whole idea is at the heart of a massive scientific effort called the Materials Genome Initiative. And just listen to its mission. It's incredibly ambitious. It's all about building the tools and knowledge we need to design a material from the ground up to do exactly what we want it to do.
And this slide really lays out the difference. The old way was painfully slow. It could take 20 years or more to get a new material from a lab into a real product. The new way, the MGI paradigm, is all about speed and integration. It's a rapid feedback loop between powerful computer simulations, real-world experiments, and huge databases. We can now design and test thousands of potential materials on a computer before we ever make a single one in the lab. It's a complete game changer.
Which brings us right back to where we started. The Stone Age, the Bronze Age, the Iron Age, each was defined by a material. The Space Age was made possible by advanced ceramics and composites. So as we learn to design matter itself, atom by atom, the real question is, what's next? What great challenge? Is it clean energy, better medicine, sustainable living? What problem is going to be solved by a material that, right this second, only exists as code inside a computer?